Thanks a lot. So again, let me start by sharing my screen. So I hope everybody can see this. Yeah, so during the last days, we talked a lot about successes of deep learning. We saw, I think, very intriguing examples. We saw some mathematical directions towards understanding why things work that well. And but last lecture was already about robustness issues, which, as we saw, sometimes cause already some serious problems. And so this lecture will be devoted specifically to limitations of deep learning, because that's also something I think we need to discuss and consider and see whether and to which extent these limitations can be also circumvented. Yeah, as I said, we saw many successes over the last days, and also in general. If you look around us, for instance, in the public sector, with self-driving cars, also new robots, which are also day-to-day helpers, telecommunication. Then in, let's say, a bit more sensitive areas, like, for instance, the law, these methods are also starting to be used, and then the whole area of science, in particular also medicine, where things are, based on deep learning algorithms are very successful. Now, on the other hand, we already discussed yesterday that there are also some downsides which we need to be certainly aware of. Robustness was the topic of last lecture. Explainability, we also already discussed. So right now, to some extent, deep learning-based algorithms are still a black box, which requires certain methods to access, let's say, the reasons why decisions were taken, but we are not there yet that we are fully confident. Then certainly the severe dependence on data causes its own problems, for instance, concerning fairness issues. Then, typically neural networks are learned and trained for a specific task, but if one looks around us, and artificial intelligence should be actually about multitasking like we humans are. And then also reasoning. So, what one would like to do is one would like to also be able to interact in a much more closer manner. So let's one time go through those problems. This is, as I said, the topic which we discussed yesterday, what we certainly aim for. And right now, this is still a limitation, is that robustness problems should be detectable and also avoidable. Heuristic approaches don't suffice because, for instance, in industry standards, you need to have certain certifications. So there, you need to have, in a certain sense, provable robustness. The question is complete robustness at all possible in all instances? We then saw also the result concerning inverse problems, which maybe raised a bit of doubt whether this is always and every instance possible. So this is certainly right now, one of the main limitations. And we also already saw this picture where one could see that with adversarial attacks, one can completely switch decisions. But for instance, here, the doctor who looks at these pictures doesn't see any difference. The second is, as I said, explainability. So right now, it's more or less like a black box. We don't have much possibility to interact with the neural network in a sense as you would interact with a human. So as a requirement I pose here, or it would be possible to ask any question about a decision, and then the answer should also reason as a human. This certainly requires then connecting deep learning to natural language processing, which is an extremely active and exciting area. Still, it's the question how far we can get by this, and whether it will be in the future indeed possible to interact with a neural network or with such a deep learning based algorithm like you would reason with a human. The severe dependence on data is another problem. So it's a pure data-driven approach. For inverse problems, we see that we can actually couple it also with domain knowledge, but in its core form, it's severely data dependent, and this causes also limitations. For instance, for applications where you don't have these large amount of data, like for instance in medical imaging. There it is often a tremendous problem to actually get access to such large amount of data. And there are methods certainly to compensate for that. So for instance, data augmentation, which was already discussed in one of the question sessions, where you basically take your training data and then you apply some operations to it. For instance, you rotate it, you scale it, and then use this as additional training data. So you artificially, in some sense, enlarge your training data set. But the question is, I mean, whether this to a certain extent can compensate this fully, because I mean, this training data, which you then augment, I mean, it's the question, I mean, how much better a covering of, let's say, the data manifold you truly get by doing that. Yeah, so this in a way calls also for, let's say, more smart methods, maybe also requiring more domain knowledge. Then problematic data. So data can be unknowingly be biased. So also uncertainty in the data can occur, which we might not be aware of. And so all of those are, again, serious problems. So I mean, I'm sure you saw all these articles about biased training data, where the algorithm, the training algorithm, then to some extent even amplified it. And this is certainly a tremendous problem. In particular, for instance, if you reach decisions based on suggestions by the neural network, for instance, if it comes to lawyers and the law, I mean, then you certainly would like to have something which is unbiased, but here problematic data can cause these issues. Yeah, and so I mean, here there are just a couple of, let's say, headlines which you could read in the newspapers, which showed that often, let's say, the sometimes even racial bias, which is in training data, is then amplified and can be found in decisions of the neural network. And so then, I mean, going further than that, as I said, a neural network is trained for a specific task. And so the question is, can we do it also for multiple tasks? The network should be able to reason. Maybe even there's this catchy phrase of lifelong learning, which one would also, to some extent, later on expect if really, I mean, a network is something like artificial intelligence. And so the question is, I mean, is this possible? Are there fundamental limitations which constrain us? So these are some issues which one need to be aware of. I mean, in this whole area, I mean, there's a huge amount of possibilities for improvement. What I would like to focus on in this talk is what I think maybe from a certain viewpoint an even more serious problem. So if we look at theoretical analysis, I mean, what we saw over the last days is that people focus on expressivity, so approximation tasks, approximation results for architectures of neural networks, conversions of training algorithms, generalization abilities, and so on. So what was, I think, to my mind, not enough focus on is what happens actually really in practice. So what is the true practical performance? I mean, if you really compute it on a computer when it's trained by modern approaches. Also, what is, yes? Okay. Yeah, I just heard that someone said something, but maybe not. Yeah, so or also what is the required sample complexity for a specific problem coming from applications? And in addition, we compute everything on today's hardware, on a computer, so there are limitations for that. So that brings us into the area of computability. There may be limitations which one need to be also aware of, and which maybe even more restrict the use of such approaches. And so in general, I think there's a theory to practice gap, where these results are certainly very nice, but it needs to go, to my mind, a bit more also in this direction. And so what I would like to do now, mainly in this talk, is to examine also the boundaries which are imposed on us on digital computation. Because there you can actually really do mathematics and rigorously analyze where there are limitations and where we stand at this point. Okay, so what can actually be computed? There's a whole area out there, computability, which provides us with a lot of tools for analyzing to which extent something is computable, how it is computable, and so on. So what is in general, and this is an informal definition, what is a computable problem? Well, I mean, that's a problem where I have some input, object, data, some output, and this can be computed with a digital machine where we are computing on right now for any given accuracy. Yeah, so that's the main point. Any given accuracy, this problem can be computed. Yeah, so that's what we want. So this raises then some questions. I mean, first of all, I mean, what one can ask, I mean, if we look at a problem, general problem, which we would like to solve, is the underlying problem feasible? So what we certainly need for that is we need to be able to compute the ground truth. So wherever we get from, I mean, it needs to be computed on the digital machine. Then when we would like to solve things with a neural network, we need to be able to compute the neural network. In particular, also compute the parameters, so the training procedure. And remember, I mean, we wrote down stochastic gradient descent, but it's something different when you then actually compute it on hardware. Yeah, so that's another step. And also, if we solve our minimization problem, can then the neural networks be actually found with arbitrary accuracy? And so this requires computability of the mapping from data to the approximation. Yeah, so all of those parts require knowledge about computability, about truth of the network, and then also of this mapping. And this figure here shows you what we certainly always aim for. We have some true signal, and then the computed signal, we should be able to give error bounds where the computed signal definitely will lie in. Okay, so why does it matter? So what could happen? So from a computability viewpoint, what could happen is, I mean, the ground truth could not be computable. Yeah, then we already have a serious problem, because then, I mean, I will not get an approximation scheme, because, I mean, if I cannot compute the ground truth with arbitrary precision, I mean, what does it mean approximation at all? Yeah, so it can also be possible that I'm not able to compute the network itself. Yeah, so that leads me to the fact that then if I cannot compute it, I mean, I don't know what, if I get something out, what this object, what this network actually does. Or, I mean, this mapping could not be computable. So the mapping from the data to the approximation, I mean, then the learning is not feasible. So then there's no way I could actually construct a learning algorithm. So what we certainly would like is you would like to trust the output of a computation. And so what we aim for are computability guarantees, which then also give us error bounds. And so this relates also to reliable AI. Because, I mean, that's what you certainly at the end of the day need. You need error bounds, which give you trust in the outcome. So that's in a way the core of trustworthiness or reliability. Yeah, and so for instance, also being able to construct error bounds, if you look at applications like, for instance, electron tomography, there people are right now still very hesitant to actually apply deep learning methods. Why? Because they actually don't really have a ground truth. So they need to rely on some error bounds, which you get. Otherwise, I mean, it's out in the open air what you compute, and they are not able, or there's no trust in the outcome, in particular if you are an uncertain domain like in electron tomography. Okay. But we certainly observe, even sometimes if the problem is not computable from a computability viewpoint, it can be certainly tackled successfully in practice. But one need to be aware of that in that sense, in that case, I mean, we could have limited precision. But if that's okay, I mean, then certainly one can also go ahead with such problems. Yeah, but still, I mean, one need to be aware of if one can show that the problem is not computable, then there's no way we can get guarantees for correct. And so that's certainly, I mean, a problem which I guess I hope all of you agree would then cause its own problems. Okay, so computability is important. As I said, I mean, there's a whole theory out there on computability, and right now we compute everything on digital computers, and the abstract idealization of that are Turing machines. Yeah, so ideally, I mean, what you have is you would like to compute some usually continuous problem, but you can only do it on the digital computer, which corresponds to, as a model, Turing machine, and so this leads us to a discrete problem. And so the question is, I mean, whether your continuous problem you can actually solve and compute with a Turing machine. If you can't do that, and if you can prove that that's not possible, then, as I said, there's no way you can get any guarantees for your computation on your digital computer. So what is a Turing machine? I mean, it's actually a really complicated and technical definition if you want to write it down precisely. So I would like to stick with this a bit more intuitive definition for the moment. So what is a Turing machine? It's a very, very simple model of computation. It's a very mathematical model. As I said, you can write it down with states and so on and so on. It's extremely technical if you really write it down precisely. But intuitively, it's a mathematical model of computation. So that's what we want. It's the typical model for the hardware we are using right now. So it defines an abstract machine that manipulates symbols on a strip of tape according to a table of rules. So we have this finite state machine, and then we have here our tape and some rules, and depending on the rules, this machine, this Turing machine, manipulates that. Yeah, so that's a very, very easy model of computation. Certainly, I mean, in cells we have a finite area. Yeah, and the tape is here in. Yeah, so this head basically moves around and manipulates the symbols. And so right now this is considered to be the classical model for computation for digital computers. So this leads us to computability, computable real numbers, and then also computable functions. So what is a computable real number? A computable number, real number is, well, one for which the following property holds. So there need to be a Turing machine, which does the following. I have an n on my initial tape, and then the Turing machine starts operating, and then it terminates with a rational number, because it can only, let's say, output rational numbers, a rational number which has a distance of this real number up to 2 to minus n. Yeah? So that's what a computable real number is. You give the precision, so there's an overall Turing machine which for any precision computes a rational number with that precision. Okay, so that seems very reasonable. There are a lot of, let's say, sets which are computable. So the set of computable real numbers is countable and dense. Irrational numbers can also be computable. But I mean, maybe also on the other side, there's no algorithm which decides, for instance, whether two computable real numbers are equal. I mean, one problem with Turing machines could be also that they don't terminate. Yeah? So they need to stop at some point. There need to be a stopping criteria. So they cannot run forever. And so therefore, sometimes things are not computable. Okay, so these are computable real numbers. Now, what is a computable function? A computable function is defined in the following way. We have an algorithm, so again, a Turing machine, which we call gamma f, which does the following for any now computable x. Yeah, so we just defined what that is. For every computable x, for every accuracy, I get an approximation of f of x in this way. Yeah, so I have my computable entry x or variable x. I have my accuracy n, and then the Turing machine computes this object here, which has this property. Yeah, also, this is very reasonable. So a function is computable if I find an algorithm so that for each computable variable x, I find a value, and for every computable x and for every accuracy, I find a value which is as close to f of x, depending on this accuracy. Also, this I think is quite reasonable. So if you look at it, I mean, minimal requirement for such an algorithmic computation is the following. The algorithm takes the input, computes the output, and there is a certain precision depending on the input precision, so also on this end. Yeah, and so this definition of computable functions we can extend, and I don't want to make the talk too technical, but we can extend it to the multidimensional and also complex domain situation. There are certain functions which are not computable. For instance, first is quite obvious. If you have a constant function which is equal to a non-computable number, that will not be computable. For obvious reasons, also discontinuous functions are not computable because of these jumps. Okay, so now we know a bit about Turing machine as a model for what we can compute right now on digital hardware, and we know what computability in a certain sense of a function is. So why is this all important? Let's maybe look at it again in a bit more detailed manner. So let's now assume I have a physical model, and I would like to model this on a digital computer. So I have my S, my model, and now I assume that there is also a mathematical model which describes this physical process. And so what I would like now is certainly I would like to analyze, because I would like to use this mathematical model. Yeah, so that's what we usually do in mathematics, modeling. We have some phenomena and then we model it, but then we need to check how good our model does. And then once we check that it's a good model, then we can use it in the end for also getting outputs and in a way, yeah, for instance, for simulations as well. Okay, so the question is then, I mean, if I have my mathematical model for S, how well does this model describe our physical process? So what would you do usually? Well, I mean, you take a lot of input signals, you compute the output here of your physical system, which you can do experimentally typically, and then you would like to compare these measurements with the prediction given by your mathematical model. Yeah? So again, you would input these signals now in your mathematical model, and then you get a prediction, and you would like to then check how close this is to Y, to get an idea how good your mathematical model is. Yeah? So this is through numerical experiments, this is through real world experiments. But here, I mean, first of all, I mean, you input it in your mathematical model and you get something out, and then you would like to compare it. And the problem you now often have is that this is not a closed form solution. So to compute this, you need to use an algorithm. Yeah, so you need to do it numerically. Okay, so you need to compute this output, and then hopefully, so you compute this output, you will get an approximation only, because so the computer can only give you an approximation of the true, let's say, theoretical prediction which you actually want, but of which you don't have a closed form. But now, I mean, you have the problem that you need to know this prediction which you got out from your algorithm, how good and how close this is to this prediction, which you cannot compute precisely. Yeah, and you computed this prediction algorithmically on your computer. So what you need to do is you need to control this distance algorithmically on the computer. And so if this is not computable, then you have a problem, because you actually don't know. I mean, so this, what you computed here could be very far from this. And so this makes it meaningless, basically, to compare these two. And even worse, if you cannot compute this approximation, if you cannot compute this distance, then, I mean, you have no idea how good your mathematical model does in comparison to S. Yeah. So this you do in real life. I mean, it's a real world experiments. Here you can only compute this typically on a digital computer, but then you need to know what you get out, how close this is. And if you cannot bound this error, if this is not computable, you don't have any knowledge about how good your mathematical model is. So this is an obstacle which you cannot break. Good, so let's look now at a very specific problem class. So the function needs to be computable in the end. We will look here at inverse problems. And yeah, again, I mean, we saw this already yesterday, this exact picture, which already showed that for inverse problems, I mean, there are sometimes obstacles one need to take care of. So what we see here, let me run you through that again. If we have small changes, I mean, then the reconstruction might change dramatically. Yeah, so the inverse problem was something of this type. We are given a matrix, so a measurement matrix. We are given y, which are the measurements, and from that knowledge, I would like to recover my initial image. And so the measurement process here is taking the Fourier transform and then samples. Okay, so this will be the general problem we will now consider. So again, I mean, it's solving a linear system of equations. I have my x, which I don't know yet. I take measurements of it, and then from knowledge of y and a, I would like to recover x. And so a is a sampling operator. I mean, typically it's highly underdetermined. There are various successful approaches to tackle this. And so one of those approaches, for instance, the sparse regularization technique, which we also already saw once, looks like this, where I aim for that the y, which I recover, is within an error range, with the error range close to my measurements. So ax is close to y up to the range of the error. And what I minimize and what I impose on my x as prior knowledge is that the L1 norm is small, so that is a sparse. So that's a very classical way to solve and tackle this problem. So, I mean, what you need to do for that is you need to be able to compute this set. So you need to solve this minimization problem. And let's call the solution set capital psi a y. So it depends on a, on this matrix, and on y. So the question is now, what can you and how and to which extent can you actually compute this on digital hardware? And in that sense, I mean, if you would like to solve this now with deep learning, so here you have a very specific form, but now you might want to compute this form, this by a deep learning type approach performed on digital hardware. And so in general, I mean, the question is, do there exist algorithms of that type at all? So can we train a neural network to solve this problem? Or is there some inherent restriction which we, if we use that type of hardware, cannot overcome at present? And so again, I mean, here's the basic flow diagram of the deep learning approach. So from the input data, as we also saw, we generate our training data. We get a representation, then we need to get a learning algorithm, which then gives us the weights and the biases. On the other side, I mean, we have explicit algorithms to compute this output. And now the deep learning approach aims to, in some sense, learn how to get from a training data now to the true output. Good, so there's a bit disappointing news now in that regard. And again, let me say, so there's a solution set. What we could prove is that this function, you see here, is not computable for a fixed parameter absolute. So what does this mean? That means on digital hardware, you cannot compute it with arbitrary precision, which is, as you hopefully agree, a serious problem. So this shows that in a certain sense, I mean, yeah, so you're in the situation which is here. Yeah, so you have your true signal, but the computed signal can be out of some range and you cannot really control it. Yeah, and so that this is not computable means certainly also automatically, if you use deep learning type approaches, this is not computable. Something a bit more is even true. It is even what one says Banach-Mazur, not Banach-Mazur computable. So that's a bit even weaker notion of computability. And let me, without going too much into the details, walk you through that as well. So again, I mean, I take a function and one calls it Banach-Mazur computable if this F maps computable sequences to computable sequences. And you see here, this is again, the C indicates that these need to be well computable numbers. Yeah, so that's, and one can show if a function is not Banach-Mazur computable, then it is not computable with respect to any other notion of computability, including the traditional one, the Turing computability. So this makes things even worse. So this is the weakest form, and so the theorem also holds for Banach-Mazur computability. So that means it is definitely in no way computable, or you're in no way able to compute this function with arbitrary precision. Yeah, so that's certainly, I mean, maybe not that nice, a bit disappointing. So how do you prove such a result? Let me just say, because again, I mean, this is quite technical. So this, for instance, one core lemma where you have some hypothesis so that in the end, I mean, the map is not computable. I mean, what you see here is in this set, you have to basically construct computable sequences which satisfies these two conditions. You see what happens here is that there are two sets, so that if you move over elements of the set, then the distance is always bounded from below, and these sets are defined in such a way that if I apply this function to my sequences, then they lie in this set. So that shows something now about the images of these sequences, these computable sequences under this map. And then there's also something like a limit point, and if these conditions are satisfied, then this map is not computable. Yeah, so I mean, but again, I mean, this if I go back, it's quite technical. These type of results, very constructive in a certain sense. But in the end, I mean, so this is what you can show, that this function is in no way computable, and so this is phrased in terms of Banach-Mazur computability. Now, let me say, before we come to the consequences of what such a result now entails, let me say that there are also very, very exciting previous results, which I would like to highlight. So there's very interesting work also on classification and also inverse problems, which show also non-computability of something similar to what we did. So these approaches employ what's called an oracle Turing machine, and I would like to briefly discuss what the differences are, and so set things into relation. But I mean, let me again highlight, I mean, these were basically, I mean, the first results which showed something in this direction. So what is this oracle Turing machine? Turing machine we already saw. Now an oracle Turing machine is to some extent an extension of regular Turing machines. They have an additional tape, the so-called oracle tape. And so this oracle tape is quite nice. So if I have a real or complex number, it gives this Turing machine access to a rational approximation with arbitrary or with demanded precision. So this is certainly, I mean, a strong assumption. So this Turing machine has access to real and complex numbers in the sense that it always gets them with arbitrary good precision. So what is the relation to, let's say, normal or classical Turing machines? Well, these oracle Turing machines, as I think one can imagine, they exceed the potential of regular Turing machines because they have this additional tape. So they are a bit more powerful in that respect. Still, I mean, on the other side, because we are interested in non-computability, one also has to say that they omit the problem that not all complex numbers can be arbitrarily well approximated. And so we already discussed before that, I mean, for real numbers and so on, I mean, computability is also an issue, whether you can indeed get approximations with arbitrary precision to those. Okay, so taking that into account, what was then shown is that we now assume, since we assume this oracle Turing machine, that we are given arbitrary accurate approximation to any complex numbers, and also in particular training samples, which could be a problem, because I mean, if we have training samples which are maybe not computable, then this might be to some extent not a realistic assumption. And so under this condition, then these results show that, or analyze whether there exist algorithms that give accurate neural networks, or whether there are computational barriers in the training of neural networks. And so what is there shown, and as I said, I mean, these are the first results of that type, that indeed, I mean, in that sense, now in the sense of this oracle Turing machine, it is not possible. Though what one can ask, I mean, these oracle Turing machines, are they a realistic assumption? So that's certainly debatable. And let me just show you one aspect concerning this as an example. So we are right now again looking at an oracle Turing machine and would like to analyze whether I can compute a certain function. So whether a certain function is computable. Now the function I choose is very special. If the input is a non-computable number, then I assume that f exhibits a behavior that prevents the computation by means of a Turing machine. Okay, so that I can do, and on the computable numbers, the function is well behaved and I can compute it by a Turing machine. So that's my function, which I would like to now compute. So then, I mean, one can show that f is not computable. I sometimes hear something from the, I think from the room. Okay. So then, I mean, we can show that f is not computable by an oracle Turing machine because of this part here, but a regular Turing machine, which operates just on those numbers, is able to compute f on its natural domain. So in that sense, I mean, non-computability of a function on a Turing machine is strictly stronger than non-computability on an oracle Turing machine. So in that sense, I mean, and as I said, I mean, this Banach-Mazur computability is in some sense, the strongest result you can achieve for non-computability, because it's the weakest form of computability, whereas Oracle Turing machines are the strongest. And so in that sense, I mean, yeah, I think it's worth a debate whether and to which extent these Oracle Turing machines in the end are the best model for real-world computations. Okay, so let's now look at some consequences which these type of results in general have. So, I mean, what we saw is that this map cannot be approximated to an arbitrary accuracy on digital computers. So we don't know if we would like to now solve this problem by learning type approaches, what we get, how good it is, what we achieve. Yeah, so as it says here, no algorithm exists on which, so if I have now a neural network and I would like to learn a neural network which approximates this, then I cannot find any algorithm which gives me a neural network which approximates this map with arbitrary accuracy and also for all measurement matrices A. Yeah, and so in that sense, if I now train such a neural network, which we do each day and all the time, still, I mean, one need to be careful and say that the output of such trained neural networks is not reliable, because and reasons I trained it on such a digital hardware. I can show that this is actually, it is not possible. There's a fundamental barrier and I cannot give error bounds. Yeah, so this is a barrier for solving finite dimensional inverse problems with neural networks, which in the main two ingredients which causes this, I mean, first of all, certainly the structure of the problem, but then also the fact that I computed on a digital machine, so on a Turing machine. And so there I can show that if I go that route and solve these problems that way, then I cannot get precise error bounds. Okay, so let's take a look at some further remark. I mean, certainly this is only for these finite dimensional inverse problems. I mean, certainly believe that it is true in much more generality, and there were also some results, as you saw before, on classification problems. It's, I think, a general problem how far you can extend these results of non-computability, what you can all not compute, and in that sense not get algorithms with arbitrary and provable accuracy. Yeah, but still right now this is for very specific problems. The problem itself is also inherently connected to digital computations. It could be that there are other platforms where things work much better. Yeah, so these are the platforms we use right now. This is our computer which we work with each day. But I mean, that doesn't mean that there are not other ways of computing which can tackle this issue and where things then suddenly become computable. And I mean, this by no means that deep learning is not impressive. I mean, it gives truly impressive results. What these results show is that there are some limitations and that one need to be aware of that. And so there need to be some, let's say, necessary caution with which one can then consider the results one obtains. Yesterday, I mean, we talked about instabilities and non-robustness. It could also be that this fact, which we just discussed now in a bit more depth, that this also leads to a certain extent to these instabilities and to non-robustness. Because as I said, I mean, we cannot estimate for these certain types of problems, I mean, the accuracy, we cannot get error bounds, and so that could also lead to such phenomena like these instabilities and non-robustness. But this is just intuitive, yeah, so this is just a guess. I mean, there's no result which precisely states that. So therefore I say it could point towards that. Yeah, and so there's also, I mean, a subtlety one need to be aware of. I mean, certainly, I mean, if we have, let's say, a fixed precision, I mean, then an algorithm sometimes could be derived, but here what we look at is, I mean, that we have one Turing machine which then computes it for any precision. So yeah, so if we are interested in different precisions, then it could be that, I mean, we need a different Turing machine for each of those precisions. But what we looked at here at the problem was we wanted to have one algorithm which could solve this problem with arbitrary accuracy. Okay, so where do we stand, and where does it take us now? Right now, I mean, everybody of us, in particular right now, those people in front of Zoom, you have a digital computer in front of you, so you compute things on digital hardware. And that's mostly exclusive. So the question is, are there other models of computation which could give us, let's say, hope that we can actually break this barrier and then maybe even could prove computability of all those problems for that specific hardware. And so there are some emerging hardware like neuromorphic computing, biocomputing. All of those are in some sense approaches which are much more closely linked to the human brain and try to mimic the human brain in a much more detailed manner. Remember, I mean, on Monday when we looked at the core definition of neural networks, we said that neural networks are also inspired by the human brain, and they certainly are. Yeah, but in a very simplistic manner. So we had these artificial neurons, which were very simplistic modeling of each neuron, and then we concatenate those to get our neural network. But in fact, I mean, if you look at the human brain, I mean, it's not a feed-forward network at all. I mean, there are some stochasticity elements in, I mean, the neurons fire in different directions, and so on and so on. It's much more complicated, certainly, I mean, than what we modeled on Monday. And so these new emerging types of hardware, for instance, aim to mimic this in a much more detailed manner. And so one can also think of different models of computations and so on. And so then the key question which one would need to answer is, I mean, does the non-computability result also hold for different computing models, or maybe not? So maybe one can actually rigorously mathematically prove that on those things work well, and we can actually compute those problems which we could not compute. Okay, so let me conclude the talk. I mean, so this was a talk in general about limitations. We discussed several limitations at the beginning. Most of those were already discussed in previous talks, like robustness issues, the question of explainability, that our neural network is more or less like a black box. Severe dependence on data, I mean, in its core form, without using too much domain knowledge. We entirely rely on the data which is given to us, and then the question is, does it work for the application we have in mind? For instance, medical imaging, do we have enough data? Do we have maybe biased data? Questions of this type, do we have uncertain data? And so the data acquisition and data modeling is an extremely important part also of the deep learning, so the data preparation, which to my mind, I mean, sometimes there's not put too much emphasis on, but I mean, it certainly should be. Specific tasks, I mean, it's usually turned to a specific task. Also reasoning is sometimes, I mean, it's still a problem, lifelong learning. So there are a lot of, let's say right now, limitations, issues, which one would need to think about when one would like to bring it to the next generation. And so then, I mean, we delved a little more into computability, and we saw that, I mean, right now we compute everything typically on a digital computer. So if we train a neural network, so therefore computability, it's important to actually study. And what we analyzed were here, I mean, specifically finite dimensional inverse problems. And I mean, maybe a bit disappointingly, one could show rigorously by showing this non-Banach-Mazur computability that there is not an algorithm which performs the training of a neural network on on digital hardware for this particular problem for any given accuracy. But I mean, it opens the door basically now also to new computability models, and which then also requires mathematical analysis. And so let me stop here and thank you a lot for your attention.
Okay, thank you very much, Gitta. Do we have any questions? I mean, perhaps first of all from the physical audience. Okay, I think we had a couple of questions in the chat. Okay, so the first question is, how do the computable real numbers relate to the Turing numbers, i.e. the numbers for which a Turing machine can be constructed that gives the digits in some base expansion?
Yeah, I believe they should be I mean, I believe they are even the same. I mean, I would need to check that. I mean, it's a new area I work in, so I cannot say for sure at the moment. But I mean, I would believe that it should be actually similar, so they should be the same.
Okay, thanks. Next question is, are there also results on computability or non-computability of classic methods for inverse problems?
Well, in a sense, I mean, so what we showed is, I mean, you remember, I mean, we called the solution set psi of AY, and so in that sense, that shows, yeah, so that's also a result about computability of inverse problems in general to a certain extent. Yeah, so if you go through, I mean, the argumentation, I mean, we defined the solution set of this minimization problem as capital psi, and so then we showed that this map is not computable. So that in that sense, it's also a result about computability of inverse problems. Now, in general, so you mean in general of inverse problems? Yeah, I don't know. I mean, there could be results. It's I wouldn't view it too likely, because I think these areas like computability and yeah, like for instance partial differential equations and inverse problems, they are not that connected then, to my mind they should be. And so I think it's not a natural question in some sense. So if you derive an algorithm for solving inverse problem, if you derive an algorithm for solving a partial differential equation, it's not immediate that people ask, is it actually also then computable on digital hardware? So in that sense, I don't think there are that many results in that direction, although to my mind, I mean, it would be very interesting and also relevant to achieve that.
Okay, thanks. Natalia is asking if you have any references for the Banach-Mazur computability and how these results have been used.
Yeah, so we have a paper on arXiv where, yeah, so maybe I could put it also in the chat, where all the references are in.
Thanks. Next question is, does quantum computing hold any promise for computability?
Sorry, I was just busy finding the paper. Could you please repeat it?
So the next question is, yeah, does quantum computing hold any promise for computability?
Okay, yeah, that's also an interesting question. So that's a different direction. Yeah, sure. I mean, so that's another path. I mean, there's this neuromorphic computing, then quantum computing. Yeah, so it could be also that gives, let's say, the step which one needs to go from non-computability to computability.
Okay, I think the last question is Natalia again asking if the lecture slides are going to be available.
Yes, absolutely. I mean, as usual, I mean, I will send it to, I think, Claire. I can send it right away. And then I think it will be uploaded if I.
Okay, so Corolla just informs me that some of the slides at least are already available.
Yes, I mean, all from the previous days, they are all available at this point, yeah. And I can send, I mean, these slides also right away.
Okay, do we have any further questions either online or in person? Okay, that's good. I've not had to run around the room with the microphone. Okay, so in that case, yeah, thank you again, Gitta, for a very nice lecture. Okay, and we resume at 11:30, where Klaus Robert Muller is going to give a talk on machine learning for the sciences towards understanding. Thanks, everyone.